Next speaker is Tobias Ludwig from Lubis EDA, where he's CEO. The title of his talk is Bringing CI, Continuous Integration, into Formal Verification. Tobias, CEO of co-founder of Lubis, specializing in EDA tools and formal verification consulting. He got his PhD in electronic EDA from the University of Technology Kaiserslautern in 2021. During his PhD, he identified inefficiencies in traditional formal verification processes within semiconductors. This insight led him to work on an automated EDA software solution aimed at enhancing development processes and ensuring high-quality, efficient outcomes. Collaborating with Dr. Michael Schwartz and Dr. Max Bertel, he co-founded Lubis to advance formal verification. Under Dr. Ludwig's leadership, Lubis EDA has focused on automating formal verification to uncover simulation-resistant and corner-case bugs in high-risk silicon design. The company integrates cutting-edge tools and AI technologies to make formal verification more accessible and effective. Okay, over to you.
Do we need to turn it on?
You want to get the focus back on the...
When I was thinking how to start the presentation, I needed an example to illustrate my case, what CI means for me in the area of formal verification. And I don't know how, but I came up with this idea of just look at the problems, and there's this show, Family Feud, I guess most know them, where they ask 100 people and ask them a question. And I thought, okay, I just do the same thing and ask the question, what is notoriously hard to verify? And I was hoping for something that did come along my ideas, but yeah, the result was a little bit different. So apparently those are the top 3 items. I guess everybody had something in his mind. If you ask me what is hard to verify as a formal engineer, I probably think about something else than other people, but these are the top 3. And it goes on. It doesn't get better, in my opinion. Especially, I was surprised by number 8. If you've ever worked on elliptic curve cryptography blocks that take 9 million cycles to compute a key, I don't think those are easy to verify, or less easier to verify than AI ML accelerators. Anyways, I picked my most favorite topic, caches. That's where I guess formal provides a very big benefit, and that's why I want to pick it as an example for today. Okay, why is verifying caches so difficult? I guess every IP has its problem, but caches have 3 things that we continuously see where the bugs are, but also that makes them hard to verify. So we have hazards. Obviously, if you have pipelines, nobody needs to verify a cache that does not have a pipeline. That's not a real problem in our cases. We have eviction, which can cause all sorts of problems with coherency if the eviction happens to the wrong way or in wrong cases. And then the last one, I guess that's the most common problem, is that although you send requests to the higher bandwidth memory to get more data, the data comes back completely out of order, and the chip needs to take care of reordering everything, putting everything back together, especially in cases of read-modify writes. So since we work a lot on this, we came up with a generalized methodology. And the point I want to make is that if we want to have some sort of CI integration, we need to have a generalized methodology, how we verify problems. And I think it's a good effort to think about these things. So in formal, verifying caches is actually simple. You say to the formal tool, hey, choose a specific address, and we only want to track that address. Some people call it the symbolic address. That's a theoretical term, but I heard the magic address or the chosen address. So today I go with the chosen address. So the formal tool randomly chooses a address to track, and that's what we want to implement as part of the formal check. And at the end of the day, if we can verify that property, we know that the cache works correctly, right? Because the cache only has one important task. If you read, you need to get the right data. That's the only thing that matters, yeah? No matter what happened before, every time you read, you need to get right data. And once you understand that is the most important property of a cache, from that on, you can start implementing your generalized check. So obviously every cache is different, and it makes sense to have a wide range of instructions, instructions or request types that customer have, because they have their own protocols and all those things. But at the end of the day, if you've seen enough caches, you realize that there is maybe 20 different types of commands or instructions that can go in. And then you have seen it all, because there's only so much that you can do with a cache in terms of requests. So what you need to do is you need to have a generalized component. We call it the FE cache that has its own interface. And then you have all the custom translation logic. So every time you work on something else, you need to have this translation logic, which you can see in the gray boxes. And that's a manual effort that we have to do today to translate that to the FE cache. And at least I haven't seen it, other people doing it, but the task of translation, that is something I think the LLMs are very good at compared to the classical approach that people take, where they want to have the generative AI generating everything for them. But if you ask the LLM to translate something from A to B, then they're usually very good at it. So you can automate that step to some extent by using AI. By the end of the day, you have to translate the incoming request. You have to translate the responses that come out of the block. And then you always want to track one specific check. And the last missing item that we need here is that we have all sorts of hit-miss cases where the cache cannot compute, although we only track one specific address, cannot compute the final result right away. So we need to track outstanding requests, but we're only interested in requests that are related to our chosen address, not to any address. And that makes the generalized implementation quite simple compared to the real cache implementation. But by using the chosen address methodology, we can now actually deploy a formal check, and later I will talk about why do we need those generalized components to have a proper CI flow. So how does it work? I spot some formal people here, so maybe they already know how these things work, but maybe there are some people here that did not extensively work with formal. So what's nice about formal is that the formal tool always, let's say, comes up with waveforms, but technically all waveforms are always included. The question is just which one to use to find the proof. So what we see here is this very simple case. It's a read request, and we know it's a miss. And it has an ID of 1, and it goes to an address. And address 1, that's the address that we've chosen to track. And now the formal tool has one big choice to make. Yeah. It needs to figure out, do I want to prove something for this specific request? And that it can do by the free wire. It's a wire that can toggle at any point in the waveform. But when it toggles and there is a command coming in, then we track that command. And since we know from our abstract cache that this is a miss, we also know that we need to see a read going out to the low bandwidth memory to get the data into the cache. So we also track that, because we also need to make sure if a second read is coming into the same address, in most cases, we do not want to see a second read going out to that low bandwidth memory. And at some point, the read comes back, and we know that it is ours because we can uniquely map it with the ID, and then we update our expected data. And in the end, the assertion itself is very simple. It just says, if the response comes back, and that you can see basically down here, once the response comes back, we want to see the data that we expect at the output. That's all the assertion is doing. You need exactly one assertion, and that assertion, I'm pretty sure LLM can get right first try. Yeah, it's a very simple one-shot assertion. But the actual complexity is coming up with this formal idea of building the proof. Let me give you a little bit more of a complex example. So now we have a sequence of commands coming in. It's not just one command, it's many, many, many commands. And we can see here that the formal tool did choose the last read coming in to our tracked address, which is address 1, that is the one for which we want to assert that we see the right data. We could also have chosen the first read, but in that case, the formal tool did choose the last read. And if you're into formal and you like to think about it, once you see in the read that you want to track, for which you want to see the right data, there's no more point of updating your expected data. If you know it's a hit, you know the data should already be in your system. So you stop updating the data afterwards. So we can see that there's even more writes coming in, but our FV expected data stays the same. And that has a technical reason, and that is that if by doing that, we reduce the complexity of the proof, so the tool doesn't need to consider cases where the data keeps changing afterwards, and it makes the proofs converge faster. So in this case, we see 2 responses coming back, one for ID1 on the bottom, and the second one for ID4. And again, the assertion is very simple. We know which data to expect by the time we receive the read hit. With ID2, we already have our expected data, and then all we do is assert that the data comes out. Again, very simple assertion, but it's the task of the formal tool to prove that it is always the case. And a counterexample that is actually a real-world example that we found is we get this sequence again, but this time, instead of getting the right data, we get the wrong data. So what happened in the design? There was a hazarding issue, and that actually required that specific sequence of read hit, write, read hit to show up. But anytime that happened, the tool, the IP would send out the previous data, which is the data of the write that has the light blue color. And it's a very abstract check. It checks all cases. The assertion is very simple, but coming up with this abstract ideas is the tough part. But once you have this generalized check in there, you can use it in all sorts of designs because the problems remain the same. And the tool will figure out, obviously, the trace that causes the bug, which is a hard thing to hit in DV. And by using such a generalized check, we can verify all aspects of a cache. And most other IP components that are out there, you can develop similar checks. So whatever your company is doing, you could develop those things with a formal mindset in mind, where you always need to think about what can I abstract away, what information is not needed to write this simple property. But once you have it, then you can do some nice stuff. So we do a lot of formal verification as a company, and we also are a very German company, so we like to track things and have processes and do numbers. So after 5 years, we kind of know how much time we spend on each phase of a project. And we realized that a major part, 30%, goes already just in bringing up the formal tool. And it's not about writing the load script or something. That's the easy part that you can automate, but you need to build the environment around it, right, to get reasonable input stimuli. And I would like to talk a little bit about how we use AI to help us with the bring up. I know many people now focus on writing the checkers, but the point I wanted to make, if you have a good abstract check, you got one assertion that proves it all. So generating that doesn't really help. We rather would look into how we can get the bring up done faster. So at the end of the day, I guess most DV flows look a little bit the same. And it's important to update those flows. And I guess Yassin was pitching that idea too, so I'm happy that that aligns with it, is that you want to have a streamlined process where AI does the things that it is good at and helps you hunting bugs while you code. We basically internally used a solution that runs regressions on our checks in the background while we do our coding. but I guess there's more potentially also other solutions coming out that do a little bit the same. And also the sign-off itself can be very time consuming if you do it all the way in the end. So we do, for the most part, sign-off while we code. We call it sign-off in the loop, to have a weekly update on our sign-off criteria. Now, I guess the most interesting part, and this is just something, take inspiration from it if you want to go along the same lines within your company. It's something that we picked up a while ago, and it's a little bit counterintuitive because I feel that the main way that LLMs are used is this idea of having a simple prompt that generates you everything, right? And by now everybody knows that's not working. So now people say, well, let's make the simple prompt and a complex prompt and really specify what you need so I can generate everything. But in reality, we know that the good companies write the spec once the IP is done. That's kind of what we see a lot. And so that really doesn't work for me. It doesn't make sense. We went down a different route. We looked at, well, where can we actually use LLMs with what they're good at? You feed a lot of information in, you get one simple answer out. And we wanted to have the AI to help us with our setup phase. So just wrote a simple prompt. We have a library of apps. Please select one. Please see what apps in the library actually work for my blog and create an instance for me, right? And then I can run it in a formal tool in the background. And that seems to work quite nicely because it's a precise task. There's a lot of information in and little information out. So how could it look like in practice? So what you see a lot in the code is somebody implements something. Experienced designers may spot it quite quickly what this DOT is doing. It's a simple round-robin arbiter, and sometimes we see those implicitly implementations. And yeah, we ask the LLM to see in our app library, hey, do we have something round-robin? And then if yes, instantiate it right away. So instead of having the manual task to go through the design, finding these things, the AI finds it for you, instantiates everything, and you can run the checks right away. Obviously, that doesn't have everything, so we still need to code a little bit on our own. So we want to have in the loop debugging capabilities. And then I'm happy that people are moving to the web. So I feel a good CI integration. We use GitLab internally, but there's also GitHub, Jenkins, Bitbucket, whatever you want to have. You should stay on the web. You should remain on the web. No need to toggle to servers, log into remote desktops. Everything should be on the web for the most part. All right, where does it leave us with the cache? Okay. Okay. Yeah, so if you have a generalized IP, you have your gray boxes with the translation logic generated. Then, for example, verifying caches becomes a nice CI flow thing that you can hook into your pipelines. Anyways, just want to talk about Lubis real quick. We're still somewhat of a young company, 5 years old. We're located all in Germany. It's a fairly sized team by now, so the easy, just get some pizza for everyone, gets a big stack of pizza. We only do formal verification. We do have a software team that automates all tasks that come for formal verification, and we have a big team of hardware engineers that can do formal verification. And since we only do that, I think we're doing a pretty good job at it. So I have a booth down there. If you have more questions, feel free to reach out.
Yeah. So the full PDF will go online. If you wanted to record it, the whole half an hour or whatever.
I just missed the 5 minutes I didn't have at the beginning.
Okay.
So
It's up to you. You can re-record it and we'll put it online. But okay. Anyway, thank you very much. Yeah, thank you, Therese.